Hi everybody, it's Mr. Zarzik here, and today I'm going to be talking about the spherical capacitor. So here is a spherical capacitor. I notice that you have a diagram. You can see an A and B there. So what this is this is supposed to be a spherical capacitor that we sliced in half so we can see on the inside. You see that there's this nested shell, so this little sphere that's inside this big sphere. What's in between the two is not important for now. Okay, we can just call it air. It's suspended in empty space. There's little strings on it, whatever, who cares? Okay, we'll fill in this space later. All right, what's important is that we have two metal shells. Okay, so the inner shell and the outer shell. You can see right here we're going to put 2Q on the inside shell. All right, so if I zoom in here, all that means is that we're going to have a positive charge distribution, or a sigma. Well, that's a terrible little circle there. Let's see if I try that again. We're going to have that charge distributed, and that's pretty good, okay, along the edge here. All right, and I'm going to thin this out just a little bit. Okay, so just imagine like this is just a slice. The charge would actually be distributed all over the outer surface of the entire sphere. Okay, it's just for cleanliness and clarity. Okay, we're just going to put it along that edge there. Okay, so just use a little imagination here. All right, now there's also this 3Q over here. Okay, that's on the outside shell. All right, and so what I mean is that we'd have this plus 3Q. So Q is just some arbitrary value. Okay, that part's not so important. All right, that would be hanging out here on the outside. Okay, I just want to thin this line out here just a little bit. All right, now, again, out here we'd have this plus 3Q. Okay, now I'm actually going to take this off the shelf for a minute. Okay, all of this is a bit of a side, but it's important. Okay, so I just want to focus on this part first. All right, by putting this plus 2Q, all right, on this inner conductor, what's going to happen is this is going to attract some negative charge. Okay, specifically just as much negative to the inside of this outer shell as we have on the outside of the inner shell. I know it's a bit of a mouthful, but that's just a fancy way of saying, okay, so then we're going to get negative 2Q over here. All right, now again, I got this 3Q. We'll deal with that in a second. Okay, so we're just starting with this little positive 2Q on the inner shell. So if we pull in minus 2Q, okay, well, right now there's no overall charge on the outer shell. All right, so then what that means is that in order for that outer shell to remain electrically neutral, well, that also means that there's going to be now a positive charge density out here on the outside, also of plus 2Q. See, so I mean, if we do the math right now, so plus 2 on the inside, minus 2 on the inside of the outer shell, plus 2 on the outer shell, so plus 2, minus 2, plus 2. So we're right back to plus 2. Okay, so the point is if we just start with this plus 2 on the inside, okay, we're going to induce this plus 2 on the outside of the outer shell really by just taking the neutral metal, and polarizing it. Okay, now, of course, we've got this other 3Q to deal with here. Okay, so what I'm going to do, I'm just going to make this like a dash line, I think. Yeah, kind of like that. And I'll do the same thing over here. All right, just so you can see that if we add this 3Q to the outside, okay, well, it's like they're both there. Okay, they're both contributing, okay, to this overall charge on the outside. And if I take and I add those things together, what do I get? I get a plus 5Q. See, so if we just go back over the numbers here, 2 on the inside, 3 on the outside, we get 5. Okay, so this is just a matter of inducing this 5Q on the outside, but it's really just the sum of the 2Q plus the 3Q. Okay, so that's a bit of it's an important concept. All right, we want to know how to do that, but this is really more about the capacitance of the spherical capacitor. All right, so I'll leave that. We can come back and look at it later if we need to. Okay, I just made a little copy of the same page here, and I just made the radii a little bit easier to see. So the inner spherical shell has a radius of A, and the outer spherical shell has a radius of B. All right. So in order to get to the capacitance, we're going to start with what we know about the electric field. Now, to derive the electric field, we use Gauss's law. Okay, so it's an important skill. So E dA is equal to the Q inside or enclosed over epsilon naught. Okay, and yes, outside the spherical shell, you might remember that's going to behave like a point charge. That part is true. Okay, the area that I'm interested in, okay, really is the space in between A and B. All right, it is that gap really that creates this thing that we call our capacitor. All right, so we have some gap that's in between two conducting things. In this case, it's two spherical shells. All right, so from Gauss's law, we're supposed to draw that Gaussian surface. Okay, which again, this is just a slice. You got to remember this would be like a Gaussian sphere that would be surrounding the inner shell. Okay, and that's the important part, is we're surrounding the inner shell, and the inner shell has this plus 2q. Okay, so our little charge enclosed here, that's just our little plus 2q, all right, over epsilon naught. Okay, and the little integral of the dA, okay, that's the Gaussian surface. And again, I've just got a circle drawn, okay, because we're looking at a slice, but we're talking about a sphere here. So we'd have this 4 pi r squared for the surface area of the sphere is equal to 2q over epsilon naught. So then to solve for the electric field, okay, we get 2q over 4 pi. I'm going to keep the epsilon naught there, and then there's the r squared. Okay, I'm not even going to simplify that 2 over 4 because, well, this 1 over 4 pi epsilon naught, that's the same thing as the Coulomb's constant, so we could write this just to make it a little bit simpler, 2kq over r squared. Okay, so the electric field in the space in between, okay, so anywhere in here, anywhere between A and B, is described by this function. Okay, it looks like a point charge, all right, where that point charge is represented by this plus 2q. It's actually the charge on the inner spherical shell. Okay, so once we have the electric field, all right, well, then the next step is we're going to figure out the voltage. Okay, we can think of this like green little dash line that I have drawn here as an equal potential line or a line of equal voltage. All right, if I look on the AP equation sheet, or if I just remember, all right, that the change in voltage is going to be equal to the negative integral of E dot dr. Okay, and notice I have this function over here as a function of E, and I'm going to change colors just because who doesn't like changing colors? Okay, so then that change in voltage, oops, grab my pen, is equal to the negative integral, okay, of this 2kq over r squared. That's my E function, or my electric field function, I should say. All right, dr. All right, so what's my integral, or what are the bounds of my integral? All right, well, if I look out over here, you can see that I got these negative signs on the outside here. That's that minus 2q thing we were talking about before on the previous slide. Okay, and then this inner shell has got these positive charges here. Okay, so point is that as we get closer to groupings of these positive charges, we go up in voltage. See, so like out here, this is at a lower voltage. All right, in here we're at a higher voltage. Just in general rule of thumb, we tend to, when we're doing these integrals with voltage, we tend to go from someplace farther away to someplace closer. So from out to in. All right, now we'll figure out if we, conceptually we're there when we evaluate the integral. So let me just set the bounds. Okay, so we can see it and so we can do it. So then I take the integral. So let's see. So let's pull some stuff out. So I got 2kq. All right, from b to a over 1 over r squared dr. All right, so I'm integrating 1 over r squared. So then I get my delta v is equal to negative 2kq times negative 1 over r, which is the integral of 1 over r squared from b to a. Okay, I've got double negatives here, so cancel those out, so I get 2kq, okay, 1 over r from b to a. All right, now I'm going to evaluate my integral. Delta v is equal to 2kq 1 over a minus 1 over b. Okay, if I go back to my picture here real quick, I can see that my little b arrow is bigger than my a, so that b is a larger radius. Okay, so we got b is larger than a, and because of that, okay, if I look in here, so just to give us some simple numbers, pretend like, a is 2 and b is 4, so I'd have like 1/2 minus 1/4 would be 1/4. All right, so point is if a is less than b, well, then this is always going to be positive. Okay, my charge here, or specifically my 2q of charge here, that's also positive, which means my delta v is also going to be positive, meaning my change in voltage as I go from b to a is going to go from something lower to something higher. So final minus initial, right? So we've got the bigger number minus the smaller number. Okay, a is at a higher voltage than b. Okay, and now I have this function for my voltage across my spherical capacitor. All right, honestly, if you were to guess this wrong, All right, the voltages in between, if we're going to evaluate, we'd have, X amount of volts, okay, in between the outer and the inner shell. All right, it's really not so much important here, the sign of the voltage. I mean, we've done it correct, okay, but really when we talk voltages, it's just, you buy a battery, it's a 1.5 volt battery, or it's a 6 volt battery, it's a 12 volt battery, okay, they don't really signify from like going from this terminal to that terminal. All right, where this becomes important, where the sign becomes important is when we start talking about capacitance. Okay, so then capacitance is defined as the charge per change in voltage. So how much charge can we fit across a voltage, right? So now I have a function for voltage. So I'm going to take it, I'm going to use it. Now I do have to be careful though, because this Q here, okay, if I back up, this is the Q that we started with. It's the Q enclosed, okay, by my Gaussian surface. It's the Q on the inside of this thing, which means it's 2Q. Okay, so we can't forget that part. I've got to stay internally consistent. So 2Q, all right, divided by my delta V, okay, which is just this lovely little expression here. All right, so if I bring that down, okay, notice I get to cancel. So 2Q goes away. All right, C is equal to 1 over K, 1 over A minus 1 over B. All right, and we tend to write, whenever it's a capacitor function, we don't use Coulomb's constant, all right, because there's actually a different K, okay, that we use when we get into filling in that space in between the gaps. So I'm going to it's just easier this way for later on. So 4 pi epsilon naught, that's K. And then I have this 1 over A minus 1 over B, okay, which is kind of a mess. So we don't like dividing by fractions. So let's move that 4 pi epsilon naught up to the top here, and I'm left with 1 over A minus 1 over B. Okay, now we could certainly leave the function like this. All right, capacitors though, physical capacitors, like there's no negative capacity. Okay, you can either put some charge, okay, across some voltage, or you can't. So like some points is capacitance is always positive. All right, so our function has to give a positive answer. I have a difficulty trying to figure out when I'm trying to subtract fractions like this. So I'm going to take, and just for my own sanity, make this a little bit easier for me to interpret. Okay, so let's see, least common denominator would be A over B. So if I go multiply by B, and multiply by A, I can clean this up just a little bit and hopefully make what I'm getting at a little bit easier to see. So I'd have that. So now I've got a fraction, so I can take the reciprocal. So C is equal to 4 pi epsilon naught times A times B over B minus A. Okay, and that's kind of what I'm getting at, is if I look at the denominator here, okay, from before, I can see that the length out to B versus A is, B is larger than A. Okay, so B is larger than A, which means that this down here, that's positive, which means my capacitance is going to be positive too. Okay, so that's where we have to make sure that when we have our function, it's got to return a positive value. There's no negative capacitance. Okay, so that's good. That works. All right, so I have this formula that describes this particular case. So like this would be my answer. Capacitance of the spherical capacitor, right, is that. Okay, just for fun, just so we can see it. All right, capacitance is defined as charge per voltage. Okay, so if I just want to look at this in terms of units, like what does this physically mean? Okay, so then Q, that's for charge. So then in terms of units, we'd have coulombs. Okay, and then for a change in voltage, that's just in volts. All right, so I have a coulomb per volt. All right, that'd be, what would that be? So coulomb is just coulomb, volt is a joule per coulomb. So then if I try to expand that out, okay, so then it'd be coulomb squared per joule. Okay, and of course we know that a joule comes from taking and putting together a Newton and a meter. So units of capacitance, coulomb squared per joule, or coulomb squared per Newton per meter, or coulomb per volt. Or wait, we can just keep going. Why stop now? Okay, so then Newton, what is that? It's kilogram meter per second squared times meter. So then what is that? So then we have coulomb squared over kilogram meter squared per second squared, which we can simplify, even though it's not really that simple. So coulomb squared times second squared over kilogram meter squared. Okay, and that right there, ugh, nope. Okay, we abbreviate that as F. What does F stand for? It stands for the farad, named after Michael Faraday. Okay, that's a farad. Well, that's one representation of a farad. I found this image online. I wanted you to see this really quick. I thought this was kind of hilarious. All right, when it comes to units, we express the units based upon what's convenient for us at the time. All right, so here's like a coulomb per volt, and then what we did. But of course, you can see there's all these other representations that we will talk about, but not today because that is enough. We have done what we needed to do. We have derived our equation, all right, for the spherical capacitor. So that's it. I'm done. Thank you for watching. This is Mr. Zarzik saying I will see you next time.